seriously, the fucking boomers.
True.
Like, they screwed you guys.
Yeah, they
And
did.
my generation too, in some sense, I'm sure.
Well, they keep
Yeah,
saying
you're
that.
like, yeah.
And then they're like, if you work hard enough, you'll just get a job.
I worked part-time as a waitress, and I could buy a house and feed my family, and it's like, alright.
Well, that's
Right.
cool.
Right.
That's nice.
We bought a house for $15,000.
Yeah, it's like, that car was that much, you know? It's not a good car.
Yeah, I hate cars too. I hope I never have to get a new car.
I just wanna live in a walkable city with like social safety nets, you know, that'd be so great.
I don't wanna live in the city though.
Mm.
That's the problem. I wouldn't have the like, unless I can get the squirrels to like,
Ooh, messenger
Hook me up.
squirrels.
You can
Yeah.
domesticate a pigeon.
I could
Pigeons are
yes.
already domesticated.
Yeah.
That's the problem. We did pigeons so dirty.
We did.
This is a
We
random
did.
fact, but like
Yeah,
pigeons
they're
were
just
already
like homeless
domesticated.
veterans
And
now.
yeah, and then one day we were like, we don't need you
We don't
anymore, and they
need you.
still want to help us, and we're just
Yeah.
like, no.
It's like really devastating.
It's really
For
devastating.
too long.
Yeah, no, it's terrible. And then we like say, oh, they're dirty. They're like rats with wings.
They were like served in war as like, they
Yes.
were used in the military, and now they're just like a trash bird on the street. It's kind of sad.
Down the street. Yeah, we just did really dirty.
Yeah, we did. We suck.
Anyways, abstract algebra.
This is your final. Can you integrate up to the height function?
No, I cannot.
You wish.
I wish.
You wish. All right, let's get this done. I've got a certain thing I want to tell you. So handing out. What is this quiz? Oh God. Okay, yeah. I was like wrote these like literally 45 minutes ago, and I don't understand them. Do you remember how at the beginning of the class I had you prove something like impromptu for assessment?
Oh yes.
On Wednesday, I'm going to ask you to do that again. Not for a grade, but just like, have you learned to prove things slightly better? And I'm going to make sure you do. I'm going to hook you up. So, score. Off the video. So we'll do that on Wednesday. It'll just be quick. And then I'll like tell you whatever the final's gonna be, and we can just work on that together in here. And then I'll have office hours, I don't know when, but I will. I'll tell you, I'll let you know when I'm gonna be in. I'll be in next week for you guys. Okay, cool, handed back homework. On the homework you just got back, the final homework, the last problem, number 7, nobody got it right. Was it number 7?
Yeah.
Yeah,
I don't think that's
nobody got it right.
Lied.
What's that?
Because the book
Because the book lied to you, and most of us believe the book. Christian did not believe the book.
I don't really understand why my counterexample is wrong.
Well, we can go through it.
Okay.
We can go through it. I think I remember why it's wrong.
Okay.
Oh,
But yeah, I think I do. But maybe you can convince me otherwise,
Maybe.
and that'd be cool. Yeah. But for the number 7, and this is going to actually, here's your first part of your final exam. Number 7 is now a final exam problem. I'm gonna actually take it out of the grade book too. And so if you've already got it done, because you submitted a counterexample I did not comprehend, then you've got one of the exam problems done. So number 7, give me a counterexample. So that problem is this: you've got a group G of order 155. Well, actually, what is the statement of it, really quick?
Let the whole problem.
Yeah.
Let A and B be non-identity elements in a group G of order 155. Prove the only subgroup of G that contains A and B is G itself.
Okay, so the only subgroup that contains 2 non-identity elements is the group G itself. So they tell you to prove that, but that is a lie. So in fact, you can find a subgroup that contains 2 different non-identity elements in this group. So what I think on a lot of your homeworks I wrote little hints on this, but what I would do is be thinking there's a couple elements in here of order 5, and if you can find a couple different elements of order 5 in this group, then they generate a subgroup that is not the whole group. So check that out. Just come up with a counterexample and give me the specific elements. You might, I mean, if you want, you can think of this as Z155, which is probably the best place to think about this. Because for a counterexample, we can use any group we want, and that's an easy group to work with. Does that sound okay? And I mean, this is 5 times 31. The answers are almost kind of right in front of you of what elements. And then maybe something else. I'll leave it be. I'll leave it to you to think about. I gave you this list of problems in case you were bored over the break. And I said some of these might be on the final. I'll tell you which one's not gonna be on the final. Fucking 55.
Holy shit, thank you.
Oh my god, it's horrible.
So
We
hard.
don't even have we don't even have the tools in the book. We haven't, like, there's tools that we need that they don't even talk about in
Like
the book.
halfway through that debate, yeah.
Yeah, I got about halfway through too, and then I was like, you know what? No.
That's great to hear.
Yeah, agreed. It's great to say.
Yeah.
Because it really sucked. I spent hours on it. And I thought, if I'm spending hours on this, this is not a good use of your time. Okay, cool. So let's do a quick review. Since everyone did a brain dump, no one knows what algebra is anymore. Let's do a quick, like, what the hell happened 10 years ago when we last met? Okay, so last time we had a map from G, a group G to a group G bar, and we said that phi was a homomorphism if what?
Preserves group operations from G into G bar.
And that's it, right? It just preserves the group operation. So in other words, phi of AB is phi of A, phi of B. Maybe on to, may not be, maybe 1-to-1, maybe not. That's all we need for a homomorphism. And we had some properties, and I'm just gonna put up some of the salient properties for us. There's like a gajillion of these, but if we take the identity element, that gets sent to the identity, and I think I spent most of that Wednesday before we left proving these things. Phi of G to the n is phi of G, all that raised to the n, and that is actually true for any integer G, any integer n. So any power, so including negative powers, so inverses and positive powers as well. For all G in G, the order of phi of G divides the order of G. So the order of the output element divides the order of the input element. So notice this is an upper cap on the output element order. So whatever, if you put in an element of order, so if you take G and you run it through phi, you get out phi of G. If this is order 12, this is no more than order 12. But it will be like 1, 2, 3, 4, 6, or 12. It will divide that order. So there's a couple of things hidden inside that. And then a consequence of that is that, let's see here. Yeah, so a consequence of that is that phi of G will divide the order of the original group. So thinking back to Lagrange's theorem, that the order of the output divides the order of the input group for a particular element. So any particular element spits out over here, that order of that guy has to divide the order of the whole domain group, and we're going to use these in just a bit here together, the order of that output element divides the order of the codomain as well. This is going to be important. So when you get a problem, and you will get a problem that says, determine all homomorphisms from this group to this group, here's what we're going to use. So this will be your main tool for that. We also define this thing called the kernel of phi, I think, did we get?
Yeah.
Yeah, what was that?
All the elements of the domain that are sent to the identity of the codomain.
Exactly, it's everything that gets sent to the identity. So you're thinking of things getting crushed into that identity on the output group. And we also showed that this kernel of phi is a subgroup of your domain, and it's furthermore a normal subgroup of that domain. So remember this symbol here? What does it mean to be normal? Somebody besides Christian.
And is this like less, the kernel of P is less than the G, right? Or equal to it? Isn't that part of it?
That's not normality.
Oh,
So if I have a subgroup H, and I say it's normal in a group G, think cosets. What is that saying about the cosets? Christian, what is that saying about the cosets?
So if H is normal in G, then AH is equal to HA for any A in G, which means that the cosets, like the left and right cosets for A, H, I guess, would be equal, but the elements don't necessarily line up, just like the overall coset structure is the same.
Right, yeah, that doesn't mean that this holds true for all the H's in there. Remember how we looked at left cosets and right cosets and they weren't always the same? If they are the same, in other words, they contain the same elements, like Christian said, they might not be in the same order, but as long as they have the same stuff in them, and no matter, this happens for any outside multiplication from the group G, then this thing is normal, and that's the definition of normality. And a nice condition for that is this, that if you take A inverse, and you multiply on the left by A and on the right by A inverse for all A and G, and that is actually contained inside the subgroup. So if this operation always sends you back into here, that's also normal. This is a condition that guarantees normality. It's an if and only if, in fact. So this is kind of like those inner automorphisms, right? This kind of looks like the inner automorphism. So any inner automorphism maps H back into itself. And then, let's see what else we've got. So we've got that. We've got this kernel. So this is some kernel properties, that the output phi of A is equal to phi of B if and only if A and B differ by the kernel of the homomorphism. So in general, what we have is something like this. You've got your group G, and you've got your group G hat over here, and you've got a bunch of things here. And what we do with this kernel is, first off, we look to see what gets sent to the identity. So let's say all this stuff gets crushed to the identity, right here. So there's my E. And all that stuff's getting sent there, those little dots are getting sent there. That any two of these elements are considered the same when we think of, I'm not saying this right. I need to come up with the right language. I think I need to get one more idea out here.
You could bring in like if you set, like with the phi of A is equal to phi of B,
Yes.
if you like, I guess left multiply both sides by the inverse of phi of A,
Yeah.
then you get like
That's you're proving it, right?
Yeah.
I was trying to come up with like a
the
good
intuitive
picture.
example. I feel like the intuitive example would just be like if you plug in a kernel phi to phi, that is just like
Yeah.
right because like the kernel collapses. So
Yeah, let's actually, I like that approach. So notice that, if I take that phi of A equals phi of B and I left multiply by phi of B inverse, like this, and then on the right, I'll have the identity element. So I canceled out that phi of B on the right. And then because of that exponent property, I can bring that inside here. And because it preserves operations, this essentially says phi of A B inverse is equal to E. Does that make sense? You see how I'm doing that? I brought the inverse in. And then phi of A B is phi of A, phi of B. So these two are the same by I guess I did, yeah, that top property up there. That you can bring the multiplication in to the outer multiplication. And then this means that this AB inverse is an element of the kernel phi because it gets sent there. And then in terms of cosets, we have a property that says this literally implies that this coset is the same as this coset. And we proved that a long time ago, but probably feels like we never proved it. Looking at Sophie's face, I don't know if we've ever proved anything in here, but
It's possible,
it's possible.
so they say.
Yeah, this picture, I'm gonna hold off on this picture. I got a good picture and I think I pulled it out too early. So we forget about this picture here. Except that all that stuff gets sent to the E and it was all in the kernel. And then I got one more thing that I wanna pop up here. That was a property from last time. And maybe I don't. I actually just wanted, I think this was something that I mentioned that I wanna start. This is really where today starts. This is called the first isomorphism theorem. So when Dr. Patnott says, where did you get to in algebra? You tell her, we got to the first isomorphism theorem. There's multiple isomorphism theorems. We're not going there. We're stopping here, to her chagrin. So if I've got this map phi that is a homomorphism from G to G bar, so that is a homomorphism. One of the uses of kernels is the following. I'm going to find the kernel of phi. In other words, all the stuff here that gets sent to the identity over here. And I'm going to treat that kernel, that set of things, as an entity to itself. So when I was doing this, I probably could have kept with my picture over here. So if I look at all this stuff that gets sent to the identity over here, these now all become the same. So what we're doing is we're essentially modding out any differences these guys might have and saying, and if you get sent to the identity, you're the same. We're just going to treat you as a block to yourself. So I'm going to take this kernel here and I'm going to mod it out of the original group. Now, if this kernel is anything more than just one element, if the kernel is anything more than the identity, which is certainly in here, the identity's in here, but if it's more than that, then this thing would not be one-to-one. Look at this picture. I've got a bunch of things getting crushed to one thing. This picture shows a homomorphism that is not one-to-one. But if I say, that bunch of stuff is now just one thing, and I treat it like a single entity, then I only have one thing getting sent to the identity. And this becomes my identity element itself. So I'm going to create this quotient group, and I can, because the kernel of phi is normal in G, so I can build this guy here. We'll talk about this to help you refresh your memory on it. and it is isomorphic to the image of the domain in this group here. So now notice that this thing here is actually a subgroup of G bar. It might be the whole thing, but it doesn't have to be. This is the image of the domain under the homomorphism. And just put a note, it may or may not be equal to the codomain. And I'm going to show you some applications. This is actually a very powerful statement that we can prove things with. But I thought the best way to demonstrate this to you, like how powerful this thing is with some examples. So let's just do some examples to understand this in an intuitive way. So I'm going to take a phi from Z12 to Z12. And we'll start with a simple one. And I think I actually did this one in that little online lecture that I gave, but let's come back to it since our recollection of things is a bit hazy. That's 3x. So I'm going to ask you a couple of questions. What is the image of phi? And what is the kernel of phi? Can you just take a minute and crank those out? Image of phi is, if you take every element from Z12 and multiply it by 3, what do you get? Thinking modulo 12 on both input and output. Let me know if you just need a boost or anything, you want a sanity check.
Isn't it just like all the elements of 12?
Say that again.
Wouldn't the image just be everything
Well,
individual?
so you're multiplying it by 3.
Oh, that part, okay.
Yeah,
Okay,
does that
so
make
it's like
sense?
1 times 3.
So it's just
Okay. I just-
You see what I'm saying?
Yeah,
Yeah, so it's a subset of that.
Yeah, I got you.
Yeah. So quick sanity check, you might have heard it. This image of phi is going to be 0.369. And then for the kernel, you're looking for all the things in Z12 that when you multiply them by 3, you get a multiple of 12. Wait. 15. Yeah. Huh. Well, ooh, that's neat. I don't know why I thought that was neat. That 6 goes to 6. I don't know. Fixed point. That's kind of cool. Oh, yeah. It's called rhythm, buddy. Is that all making sense up there? We're feeling yes. So my kernel is all the stuff that gets sent to 0. So my kernel is 0, 4, and 8. Let me stop. Let me give everybody a chance, because I really want, if you understand this, you've got the idea. So if you're already like there, and you're waiting for what comes next, I would ask you to, what is Z mod the kernel? Z12 mod the kernel of phi? Because that's what we want to look at next. That's a collection of cosets. Does anybody need help? Yes?
I'm just making sure I'm reading
Yeah,
the
yeah.
image correctly. So
Great.
the reason why we're saying that it's only 0, 3, 6, and 9 is because those are all of the ones that are multiples of 3 smaller than 12.
Perfect.
Okay.
Yes, ma'am. Yes. And you might want to just write out some of these cosets to, well, let's see, let's put it up here. So curve phi, 0, 5, 8. Notice that under addition, that is a subgroup unto itself, mod 12. So that all checks out. Just remember, you're doing everything mod 12. Put some hints up there just to kind of see, maybe a good way to organize your work too. For maximum visual insight. I'm wrong. Christians are like a fire alarm. Oh, wait, what happened?
It was like a fire alarm.
How, what do you mean?
I hear
Yeah.
it.
Oh, okay. I was like, what? You're seeing it?
No.
Oh, like I could open that window.
Huh. Well, the fire's not here yet. We're good. Hopefully we can finish this problem before we go up in flames. Do you notice how the cosets, remember how the cosets partition the set into distinct things? So it's basically saying, these are the same, and these are things that differ by 4. So let me stop and make sure that you're getting that. So we only have 4 items in here, and they are these 4 right here. These 4 things. So we've got 0 plus curve phi, which is those other 2 things, 1 plus curve phi. I like saying curve phi. I was enjoying saying that to myself a lot over break. Curve phi. It's a cute dog name.
That would be cute.
Curve phi, yeah. And then you know what it was. You know it's the kernel of a homomorphism.
So then, like, that's isomorphic to the integers, like, so, or mod 4, right?
Yes.
But, so, when you're writing that out, do you just write the quotient group of, like, the integers mod 12, mod curve phi is just the integers mod 4, or do you do like this set of sets, like where it's like you have a set of the set
Right.
0, 4, 8 plus, or and the set 1, 5, you know what I mean? 'Cause
Yeah.
that feels kind of redundant if you do it that
So
way.
it's not, so I wouldn't say it's the integers mod 4, cause it isn't.
Okay.
But it
it's
is isomorphic
okay.
to the integers mod 4.
Mhm.
That's the subtlety, but yeah, so I would say these are my cosets.
Is that like the way you usually write that then, without feeling like super clunky, I guess?
It does feel clunky, I mean, you could, if you needed to do a lot with it, you could adopt some information, you know,
Mhm.
some notation like this
Yeah,
to really emphasize that point.
because what you do have there is like a set of sets, right?
Correct.
Okay.
Yes, yeah. So I've been using, just for my own personal notation, those little bars, just to kind of indicate it represents,
Oh,
it's a
just
class.
like the representative.
Yeah,
right?
yeah. So let me stop, is there any questions here, any troubles with this? So now look at the image of phi. Here's the image of phi, right here. Let's put that next to this. So this is Z12 mod kernel of phi, and then the image of phi, I'm gonna put it right next to here, is 0, 3, 6, 9. Do you see an isomorphism between those two sets? What is that isomorphism? What map? What can I do? I can take the representative here and do what to it to get that? Multiply by 3. That happens to be the original map. So the original map said 3x. Take 3 times the representative and spit it out over here. And in fact, what we're going to do is we're going to talk about an induced map. So there is this induced map, an induced isomorphism. And I'm going to draw a commutative diagram that will kind of pull this all together for you after we get this done. This induced isomorphism from Z12 mod the kernel of phi to the image of phi, and it's given by psi of something from here, which is going to look like one of these guys. So it's going to be some g plus the kernel of phi. You got some representative, maybe it's 0. And honestly, you could use any of these representatives you want here for your set. Any of these, if I put 0, 4, or 8 here, it's the same dang thing. So I'm going to send that to phi, my original map of g. And essentially what I'm doing is I'm saying all the different things that would go here are now just one thing. So in other words, so if I had so psi of 0, let's do a different one. Let's do 1 plus ker phi. That's gonna get sent to 3. But also, the 5 and 9 would get there. So 5 plus ker phi, if I sent that, that would go there, and 9 plus ker phi. That all goes there. They're all the same thing, so I'm sending a bunch of different things. 3 things at a time get sent to one thing. But in my mind, this is the power of math, in my mind, those are all the same thing.
In this example, you define your induced isomorphism as just your original homomorphism,
Yes.
right? Is that always the case? Or
Yes.
that you need to, okay.
That is always the case. Yeah, and we'll always set this up. So this homomorphism, this isomorphism here is a good question, Christian. This one here will be, so I'll have this psi that goes from g ker phi to the image of g, and it's going to be exactly like this psi of g ker phi. I take a representative and just send it to phi of that representative.
Okay. And then just with that, there's
Yes,
like
sir.
the assumption that like representatives, like 0 is equal to the representative 4, so like those
So do you see how this is working? What we're doing is we've got this set of these different things. So I'm gonna go back to this damn diagram again. Let's see, I'll just do 4. Let's do 3 things at a time. So little stars, just 3 stars. Why do I keep, because I'm like trying to summon demons or something. What's new? And then we'll have some X's, 3 X's. So what I do is I take all this stuff and organize it. So I take the group and I organize it like this. And I've said that these things are all the same because this gets sent, all these stars get sent to the same place, all the X's get sent to the same place, and all the dots get sent to the same place. And then I create these 3 as just 3 entities to themselves. And so that when this used to go, like we used to have 3 arrows that went from there to some output, now I only got 1 arrow, and I've got injectivity.
In this diagram, both those circles represent the same domain space, though.
Yes,
right?
sir. Yeah,
You're
yeah.
just sorting within the domain.
Yeah, so this is like G, and then this is G mod that kernel.
Yeah.
Yes,
Okay,
yes.
yep.
Okay, let me show you a diagram to kind of pull this picture together here. And we've definitely got enough time to look at some cool examples. So the picture here is this. I've got a group G, and I've got this homomorphism. Well, actually, first off, yep. And then I've got this phi that sends me to the image of phi of G. I've got a kernel for this thing. And so I create this map, and this pi is a pretty standard representation for a projection. So what I'm gonna do is I'm gonna project everything from G down into these cosets. So this pi map takes an element from G and it sends it to G kernel phi. So it sends every element to its appropriate coset. And then this is the original map, and this is the psi map that is induced by this projection and then the original map. And that psi takes G cur phi and spits out phi of G. Kind of just good to have this picture, the schematic of how this is all playing out. So here, the pi was the thing that sent each of these guys to their new organized home, right? Pi sent those, pi's the organizer. All right, let's do another example. Is this seeming okay? Yeah, cool. If this is making some sense, then this stuff is working well in your brain. Okay, so let's do a few more examples. So, different one that will feel very close to home because you've been working with this almost since day 1, but it's a whole different perspective on it now. So let's take a maps, another example, phi, that goes from the integers to the integers mod n. And this map is going to be phi of x is x mod n. So I ask you again, what is the image of phi and what is the kernel of phi? set then, right? So, and it's not just x, right? It's because our domain is the integers, right? So what is that x in particular? Yes, yes. What's the image?
Isn't it just X mod n?
So the image should be a set.
So 0 through n minus 1.
So it's z mod n, right? It's actually, it hits everything. Yes, it is 0 through n minus 1 mod n. Yeah, but you can hit everything over here, right? Because you've literally got every possible thing you could mod n. So the image is the whole set. So that's cool. We don't have to worry about it not being onto. It's onto. But it is not one-to-one. What is the kernel?
The set of all x times n such that x is an integer.
Exactly. It's all multiples of n. Right? If that's z mod 12, then 0, 12, 24, 36, those are all 0. So it's everything that is just a multiple of n. So now the first isomorphism theorem tells me something. It tells me this. So by the first isomorphism theorem, fit, I guess we will call it, I've never done that before, but I guess here we are. It tells me that z mod nz is isomorphic to z mod n. So I used the first isomorphism theorem to prove that. And how do you prove it? You establish an homomorphism that has the kernel you're interested in. So see, if I asked you, if I said, prove this using the first isomorphism theorem, you would say, I'm gonna try this phi because I know its kernel is nz. And when I mod that out, boom, got it. Let's try another one. Questions on this one? We're good. Is that too fast? We good? No? Okay, all right. Let's do another one. So here's a fun one. So I'm going to define R star to be the real numbers sans 0 under multiplication, just normal multiplication. So that's a group. Everything has an inverse because we took out 0. If we hadn't taken out 0, it wouldn't be a group because 0 doesn't have an inverse. But this is a group, and I'm establishing this homomorphism phi from R star back into itself, and it works like this. Take your input and square it. So, what's the image, what's the kernel? What does the first isomorphism theorem tell you? So I push it one more level. So you give me these things, image of phi, kernel of phi, and then fit implies what? This might take, this will take a little bit. We'll check in for sanity checks on the image and the kernel before we'll let you get too out in left field. What is your identity element? We kind of need to know that. Let's make sure we're on the right track. What's my identity element here? One.
Because it itself.
Yeah, multiplicative identity is 1, and it still is here. So 1 is your identity. So you're asking yourself, what does phi send to 1? There's more than one thing in the kernel. What do we think is in that kernel? One or negative one. Does that make sense? Does that feel right? Were you kind of feeling that maybe? So 1 and negative 1. And that is a multiplicative group. All right? So that's your kernel. What is your image?
Just R plus.
Yeah, it folds it in half. It takes all the negatives and makes them positive. So it's the image of phi is just the positive reals. Yeah. So what does the first isomorphism theorem tell me? That R star mod the kernel is isomorphic to the positive integers. And I want you to think about that. Does that make sense? Think about what, look at that and make that mofo make sense in your head. Why does that make total sense if you're insane enough to be here at this point in this course? What does taking a quotient space do? I'm thinking like a plain English statement here. No words, no particular words. Well, what's your ideas? Oh, okay, not fit for public, okay.
It's just like vague shapes floating around. I don't think I can explain.
I need like a confession booth or something. There's gotta be some on
That should
campus who
be-
should like do math that way.
You break it into confession.
Yeah. What is it? Tell me what the isomorphism is.
Isn't it because if you do like what we did the other time, but we're using multiplication this time, it gives you all the, like, the negative one will give you the opposite and the positive one will give you like the opposite signs.
Yes, yes. This is saying that negatives and positives become identical.
Mm-hmm.
So we're saying that -1 and +1 are now the same thing. They are treated as the same thing. So minus, think about how this group works. What are the cosets here? They look like this.
That's
Right.
how I was thinking about it, which flips the signs.
Perfect. That's exactly right. So this is equivalent to this. Because you multiply the minus and you get the same dang thing. So it essentially takes the real line, sans 0, and folds it in half. And meshes that x and minus x up together. So it folds them and just gives you the positive reals. All right, let's do another one. Let's do some calculus. Let's do calculus. How about that? That sounds great, doesn't it? Sophie, I don't know how much of that you were here for.
Not much, but it makes sense.
Does it make it so? Okay, cool.
Yeah, no, yeah.
Okay. All right, good. So here's a fee. I'm very excited about this one, quite frankly. So let me explain what these groups are in a second. And when you're Algebra 2 folks, I'm kind of doing this for you too. This is the collection of all polynomials in X with real coefficients. Does that make sense? So this is all polynomials of any degree in the variable X with real coefficients. And our phi takes a polynomial and spits out its derivative, its first derivative. What's the kernel of phi? And what's the image of phi? That's right. That's right. Sorry, I'm just so fucking excited about this example. This one's weird. Like, probably your intuition will be right, but then some things are weird.
What's the group operation?
Great question. Let's do plus. Excellent question. What's my identity?
It'd be 0, right?
0, yes. So our identity is the 0 polynomial,
Oh.
which is just 0.
Yeah.
Yeah, yeah.
You mean the kernel is just any constant?
Well, if you want to spoil it for everyone, yes, I guess it is. Bro. Did everybody hear that? Everybody heard that. No, you didn't hear it. Okay, cool, good. Spend if you're good. Only Ms. Kayla heard it.
Well, I was thinking about it anyway.
Okay, then awesome. That's
She
great.
was on the same page.
You are like a coset.
Yeah,
You guys are a
yeah,
coset.
yeah.
Absolutely.
Cosets.
That's not what it is.
I get it in terms of numbers, but sometimes in terms of these, I'm like, in one ear, not the other.
What was that?
I get it in terms of numbers on how to get it and everything, but then I'm all like looking at this, I'm all like, I'm so lost.
So tell me where, so when you're lost, let's talk. Let's get
Okay.
you unlost.
So for the image, I know that it's supposed to be like if you have 3K, it's any multiple of 3 that's smaller than that of the like Z12.
Yes.
But
We don't have 3 here.
we don't have
Right?
to.
Yeah. So what are we doing? We're taking the derivative of a polynomial.
Yes.
And so let's think about the image here, right? So I take a polynomial, I take its derivative, d dx, and I get out what comes out? Polynomials, right? Take a polynomial. So if you had, let's say we had 3x squared plus 2x minus 5, what comes out? 6x plus 2. So it goes down a degree.
Mm-hmm.
Is there any polynomial over here? So this is part of the fun questions. And this is good, I'm glad, this should be puzzling. If I give you a polynomial over here, can I hit it with some input?
Yeah,
Does it matter what I put over here?
not really.
No,
There's no
really.
like upper bound on the input space, right? Like on the degree that the
That's
input
right,
space is,
yes.
So it should just be the same.
What operation takes me back?
Integration.
Integration. So if I take the antiderivative, if you tell me, solve this, phi of blah equals this polynomial, then I'll say, oh, just make blah some antiderivative of this thing. And then I can hit it. So the image is actually everything. There isn't a single polynomial here that isn't the derivative of something else. So you weren't confused. You weren't confused at all. You asked a good question. That's all. Does that make sense now?
Yeah, so just basically because the domain is like infinite in both
Yes.
cases, then we
Yes.
can just say it's the every polynomial.
Yeah,
That's the image.
exactly. Yeah, so this is an onto map, in fact.
Okay.
Yeah. So image of phi is literally that collection of all the, we're not used to working with these infinite things like this. I thought it'd be fun to like toss this in. The kernel, you may have heard about this, is everything whose derivative is 0.
So it's just Z.
It's,
Is it
slow
just
down a
all the
second.
integers? Or no, it should be all the reals?
all the reals. So any constant goes to 0. So the kernel, and if this had a Z here, then you would have totally been right. But the kernel is just the real numbers because their derivative is 0. Does that make sense? So let's look at what does the fit say. Fit says that the polynomials over x, if I mod out the reals, that is actually just isomorphic to this. But I'll tell you something else it's isomorphic to. So that's weird, but this is weird because this is infinite. So yeah, I did do that right. I thought I put x there. This is also isomorphic to all the polynomials that don't have a constant term. You could think about that. And I don't want to spend too much time on it, but it was what I realized over the weekend that was making me very happy and excited.
Would it then be just like isomorphic to any infinite group or infinite order group?
Infinite order group? Not necessarily, because with the structure, like
Or
here.
like I
is
guess
there-
with like the same operation, like if you, or,
Um,
well, I guess that also doesn't really matter.
Yeah, I would be curious. I would say this, for any n, could do that. I could prove that. Because this thing's infinite, there's a lot of room for
Yeah.
nuttiness to happen. But this is a little bit different than the things we've had.
But it does rely on then the structure of like the polynomial.
Yes, absolutely, yes,
Okay.
100%. So I wouldn't say in general.
Yeah,
this
yeah,
is
you
like-
can't like draw, yeah, okay, that makes
100%.
sense.
And in fact, think about that R star was an infinite group, right? Actually, that was an infinite group up there. We modded some stuff out and things were weird. Different here, right? Because this was infinite.
With that, would you be able to say then that like R star is isomorphic to like 2R star? Well, you should be, right?
Yeah, it is, definitely.
Yeah.
It is, indeed.
And for like the same sort of reason.
Yes,
Yeah.
yes, a scaling. It's like a scaling.
Yeah, like
This is,
isomorphism would
Yeah.
be easy to create because you could just like add the, yeah.
100%.
That makes sense.
absolutely. Cool. Next, let's do one last thing. So this is one where you're gonna have to suffer. This is one where you gotta like play along and watch and let me know if this makes sense, because this is probably the last example. But maybe I'll give you one of your exam problems right after we do this. So find all homomorphisms from Z6 to Z15. So we're pulling back a little bit. We're leaving behind the fundamental, the first isomorphism theorem. And now we're coming to a kind of more general problem. What are all the ways I can send this to this that are homomorphisms, so they preserve the group structure? And this is weird, right? Because this is mod 6 and this is mod 15, so things are very different here. But the key to all this is the following. So the key, we're gonna build a build different fees from Z6 to Z15, and all we need is to assign the generator of this domain group 1 different output values over here, and that should be 15. So we're gonna assign phi of 1 to be different values k. And we're gonna figure out what are the possible places I can send the generator of this over here that still preserve group structure.
And you only need to assign one generator, right?
Yes, but we will end up with we'll end up with a whole list of them.
Yeah, but you wouldn't need to like assign like then, right?
Well, we will have like here, I think we're gonna have 3 homomorphisms.
Oh, okay.
Does that, maybe I don't understand, is that,
I think I see what you're doing.
okay, cool.
Yeah.
And then maybe once I get it done, it'll make some sense. So when you start this process, you're just gonna figure out, you've got Z6 here, right? You've got Z15 over here, and there's 6 things here and 15 here. You're gonna take 1 and see where can I send that. And the thing that's gonna narrow this down is the following, that result that we had earlier about how homomorphisms work. So we need to ensure that phi of 1 divides the order of the input group. So order of domain. So this is the divides. Phi of 1 divides 6, and phi of 1 needs to divide the codomain order. So that's 15. This is the order of the codomain. In other words, k needs to divide 6, and k needs to divide 15. And I'm going to think of all the possibilities for that, and that's going to give me every possible homomorphism. So what are some good k's? What's the lowest k? 1.
3.
Yes. And 3, and that's about it. Now remember, this k, sorry, ooh, I shouldn't say this. I'm using bad notation here. Set this, let's leave that as k, but let's say this order of phi of 1, sorry. Yeah, that would have been not correct notation otherwise. So in other words, the order of this element k has to be that. So i.e., the order of k equals 1, or the order of k equals 3. So now you got to kind of figure out in Z15 what elements satisfy those orders. And we've got this nice little result that works like this. So use in Z mod n the order of k is equal to n over the GCD of n and k itself. This is an old result. Abraham used it pretty recently. I'm not sure if anyone else remembers it, but I know Abraham used it on something I just graded and handed back. So this you can use to narrow down what your k's are. And here's a nice form of it right here. In other words, the GCD, so find all k so that the GCD of your codomain and k equal n over the order you're interested in. Order of interest. So let's start with, let's come back to this. So have cases. Case, we have the order of k, order of phi of 1 equals 1. What has order 1 in a group? There's only one thing that has order 1.
It's or 1.
Identity.
Yeah.
The identity. Does that make sense? Yeah, the only thing, so let's make a little note here for yourself. The only thing in a group that has order 1 is the identity. Only possible thing is phi of 1 equals 0. So here I'm saying that my k is equal to 0. It's the 0 map. It crushes everything. Sorry, I put over here, I forgot to say the part. Once you know what phi of 1 is, because this is a homomorphism, you know anything is just kx. Does that make sense? And we kind of talked about this a long time ago. So once you know what this is, your whole map will just be this number here times the input element. So over here, when I have this, phi of x is just the 0 map. What's the kernel? Everything. So notice here that the kernel of this phi equals z6. It just crushes everything. It's okay, this is called the trivial homomorphism. And that'll always be an answer for you in this kind of problem. And then we come to phi of 1, case phi of 1, or order of phi of 1 is 3. So now let's look at this little thing up here. So find all k in z, z6 actually, I guess, because, yeah, I'm multiplying on the inside. Find all k in z6 such that, oh wait, no, that isn't 15, isn't it? Yes, yeah, in z15, such that, what does I got here? The order of k equals 3. So I'm gonna come to my, i.e., the GCD of 15 and k is equal, n over 3, so 15 over 3 equals 5.
So wouldn't K equal 5?
So k equals 5, yep. And what else? There's one more. And here's a little tip on these problems. The number of homomorphisms from Zn to Zm, the number of homomorphisms is the greatest common divisor in these two numbers.
Oh, could it be 10?
It's 10, yes. And so what's the greatest common divisor there? 3. So I know I have 3 homomorphisms to find. Here's 1, here's 2, and the third one is in fact, this is -5 in Z mod 15. Do you see that? This is -5. So think about this, and you're gonna see this a lot. When you get these pairs, you're gonna get something and its opposite. It's plus and its minus version. Do you see what I'm talking about here? That this is this is -5 mod 15. So now I've got my 3 homomorphisms, and they are this. Phi of x equals 0, phi of x equals 5x, and phi of x equals 10x, and this is them. So let me stop and see some processing. Yes?
Question, so why in this case is case 1 we're using Z6 and case 2 we're using Z15?
So here I was just simply noting that the kernel of this thing was the whole, so I still used Z15 in this.
Oh, okay.
But then why did we have to use 15 in the second case? Was it just because it's our codomain?
Yeah, because think of how we're setting this up. It is because it's the codomain. So this phi outputs things in Z15.
So we know it has to be in the domain. We're trying to show that it's also in the codomain.
Yes.
Okay.
I'm trying, this K can come anywhere from here.
Got it.
Okay.
And I'm just trying to pick the ones that are harmonious with this domain here. So that they have the same cadence.
Okay.
Does that make sense? All right. Let me give you one of your exam problems right now. Oh man, I had so much other stuff to show you. Oh well, I'll make a video about it. I'm sure you'll watch it. I'm sure I'll make it. So let's just, I would like to make it. Because I did want to tell you, because remember that problem I gave you, just really quick, I said Z plus Z mod 4-2. You can use the first isomorphism theorem to really nicely show that. So I'll write it up and just share it with you guys, because I could probably just photocopy this.
Is that a 4?
What's that?
Is that a 4?
That's not
That is a 4.
Okay.
4, 2?
Yeah.
Yes. Yes, yes. It turns out that this is, and you can maybe figure it out,
No, this is one of our exam problems.
turns out to be that.
So we're just showing that.
What's that?
We're showing that.
No, that's not, this is just some other fun thing.
Oh.
This was like an old problem that I gave you guys like weeks ago, that I said, think about it. But I'm saying you can use the first isomorphism theorem to actually show that result.
Oh.
This is not your exam problem.
Oh.
This is your exam problem. This one here, Cormac, if you made it to the end. Hopefully you didn't scrub past this, my friend. Exam problem, find all homomorphisms from Z24 to Z18. How many should there be?
6.
There are 6. One will be the trivial. And then the rest aren't.
And just to make sure I'm thinking of this right, they're, the greatest common divisor between the two of them will be the amount of k's that there should be?
Yeah,
Okay.
exactly. Yeah, that's right. Perfectly said.
It's so cold in here.
It is.
Yes.
Try
It's
going-
because it's algebra.
Try going in the
It's
basement.
because we're all so